Hey there, guys. We are about I want to tell you a little of a gas joke that I came across here since we're in the gases unit. Heard about helium. He walked into a bar, and a bartender said, "We don't serve no noble gases here. Helium doesn't react." Ba-da-ba. You guys get that? Helium's a noble gas. They're non-reactive. I don't know. Tyler thinks it's funny. He's sitting in here. See, you guys can see that. There you go. What's up? So, little shout out there to the chemistry students, and we're going to talk about Avogadro's law here. So, this law is talking about equal volumes of gases at the same temperature and pressure contain equal number of molecules. So, you can see here I have two balloons. We'll call balloon number 1 and balloon number 2. And this one is filled with carbon dioxide molecules, so CO2, and this one is filled with our hydrogen molecules, which is H2, and they're both at the same temperature, same pressure. They both have the same volume. Let's say their volume is 1 liter. Even though they're different elements, or actually a compound and a different compound, they have the exact same number of molecules. So maybe there's 1 mole here and 1 mole here. That is really what Avogadro's law is saying. So again, looking at that in here, this example, equal volumes of gas at the same temperature and pressure have the same number of molecules. So if I tell you my carbon dioxide balloon here in this example has 2 moles of gas, and they're all at STP, standard temperature and pressure, right? 1 atmosphere, ATM, and the temperature is 273 Kelvin. How many moles does oxygen have, and how many moles does my hydrogen have? The answer? 2. They're all 2 moles, because all gases are with the same volume. So this is volume 1 equals volume 2 equals volume 3. The volumes are all equal. They all have the same number of moles of a gas. That's Avogadro's law. So that's what I kind of stated down here in words. And we're also looking at the STP. All gases will behave the same, and they all are going to have the 22.4 liters. So this is an important thing that you should have filled in on your equation card. If you do not have that, 22.4 liters equals 1 mole. And the way we use that as a conversion factor is taking a look right here. That 1 mole equals 6.022 times 10 to the 23rd particles, and that's 22.4 liters. So let's put that to use here in some gas stoichiometry. So you can see here I have an equation. Hydrogen gas reacts with oxygen to form water. I have 2 molecules of hydrogen, 2 moles of hydrogen, and 2 volumes of hydrogen. That's what my coefficient tells me. For here, there's a coefficient of 1, so it's a 1, 1, 1. Same with water, 2, 2, 2. So how do I possibly ratio these together? And you guys remember from our other stoichiometry problems, a mole ratio. Well, we can do a molecule-to-molecule ratio, a mole-to-mole ratio, or a volume-to-volume ratio. So a possible molecule ratio is 2 H2s to 1 O2, or 2 H2s to 2 H2Os, or 1 O2 to 2 H2Os. So that's for molecules. Our mole ratios are the same. You guys already know how to write mole ratios. And the new thing here, the new thing is our volume ratio. So this I would kind of star and say this is new for our volume ratios, right? Volume is represented with V. Ratio here, a 2-to-1 ratio, same as the mole ratio, as the volume ratios. All right, so continuing on here, we have some of these volume ratios that we can put to use in our gas stoichiometry map. So you guys all remember GMA, right? Grams, moles, atoms. But instead of A, we're going to replace it with a V. Again, this is our volume now that we are replacing. Instead of atoms, I can use this right here. And again, I can do a G, M, and instead of A, again, I'm doing volume. But the new thing that we get to do here is use a volume ratio. So you can actually ratio volumes. Volume ratio is the same thing as our mole ratio. And remember that our kind of numbers that we have to fill in here. So remember our numbers here, 1 always goes with mole. Grams, you're always going to look on the periodic table. And volume, now, 1 mole equals 22.4 liters. That's Avogadro's law, kind of saying that. So the 22.4 is always going to go with the volume. 22.4 liters equals 1 mole, and we use that as a conversion factor. So let's put that to use here in an example problem. So remember, standard molar volume of a gas, STP, when at STP, it's 22.4 liters. So what volume does 5.5 moles of gas at STP have? So my given is 5.5 moles, and my unknown is going to get to volumes of a gas. Well, I bring down my moles, and I'm going to volume, which is liters, right? In 1 mole, there is 22.4 liters. Moles cancel. 5.5 times my 22. Grab my calculator to solve that out. 123.2. So 123.2. Keeping correct with sig figs, if I only need 2 sig figs, 120 liters of gas. New problem here. What quantity of gas in moles is contained in 1.54 liters at STP? So now I'm asking to convert liters to moles of a gas. So I set it up the exact same way, 1.54 liters. And again, I'm going to use my conversion. That 22.4 liters equals 1 mole. Liters cancel. And I can type in 1.54 divided by 22.4 equals 0.0687. And I'm going to round it up to 688 as my moles of the gas formed. And then the last thing that we need to do here with this is use it in a gas stoichiometry problem where we go from reactants to products. So here we're given xenon gas reacting with fluorine gas to produce the compound xenon hexafluoride. A researcher needs 3.14 liters of xenon hexafluoride, so my xenon hexafluoride is 3.14 liters is needed. It says how much reactant is needed. So I need to find out how much unknown amount of F2 and an unknown amount of iron. And when I say much, I'm going to talk about grams here of reactant. So I'm going to put the grams and the grams of my F2. So now I'm going to set up my problem here, take my given and convert it to the unknown in this problem, and we will solve really 2 of these, because I'm going to take my grams of a compound to, or actually liters of the compound to grams of this, and then liters to grams for each one. So I'm going to start off with my 3.14 liters of the xenon hexafluoride and convert that to grams, and we'll go to F2 first, and I'll kind of switch colors here. We'll go, that one will be 1, so I'll set it up in blue. Let's convert liters of xenon hexafluoride. So I do the same thing. I need to cancel my units and my compound, and I'm going from liters to moles of a compound, the xenon hexafluoride. In 1 mole, remember we just learned this, it's 22.4 liters. So liters cancel. I'm now in moles. I can go moles of xenon hexafluoride to moles of my F2, right? The mole ratio is well, this is not a balanced equation, so I need to make sure we balance the equation. So taking a look here, I have 6 F's, so that means I need to get this to a 6 by putting a 3 here. 1xe, 1xe, that's a balanced equation now. So my ratio is 3 to 1. Those cancel. I'm in moles of F2. And then my last step is to do moles of F2 to grams of F2. Knowing that 1 mole is on the periodic table for fluorine, it's 19. So that we have our 2 F's. So 19 plus 19 gives me my 38 grams. Cancels my moles, and I can then type in, going across, the 3.14 divided by 22 times 3 times 38, and we get 15.98. I'm going to round that up to 16.0 grams of F2 needed. And then let's do the exact same thing here with our xenon, and I'll do this one in blue. So I'll do this one here as 2 in orange to switch it to xenon. So I'm going to take my 3.14 liters of xenon hexafluoride and convert that the exact same way, but I'm going to xenon here. Cancel my liters of XeF6 to moles of XeF6. It's a 1 to 22.4 ratio. Liters cancel. I'm now in moles. Moles of XeF6 to moles of Xe. This is a 1 to 1 mole ratio. And then moles of Xe to grams of Xe. 1 mole xenon on the periodic table is 131.29. And I can simply multiply and divide here. So 3.14 divided by the 22.4 times 131.29, and I get 18.4 as my grams. 18.4 as my grams of xenon needed. And those are your 2 answers there for the mole conversions.